Okay, so today we're going to go over the periodic trends, basically just patterns scientists have found in the periodic table. Okay, so the ones we'll be looking at are atomic radius, ionic radius, reactivity, ionization energy, and electronegativity. So, what is atomic radius? Basically just saying how wide an atom is from its center, the nucleus, to its outer edge. So, scientists have found these trends as the number of protons increase, say going from like 19 to 36, increasing protons, the radius gets smaller. And you'll see that right here. So, why is this? Because in an atom, the protons are constantly pulling in the electrons on the outside. So more protons would equal a stronger force, making the radius shrink further. Okay, so back to the periodic table. As you can see, they're also getting bigger going down. So with hydrogen and francium, they get bigger because the valence electrons are so much farther from the nucleus in francium that the nucleus has a harder time pulling the electrons in. Okay, so ionic radius. What is an ion? An ion is when an atom loses or gains an electron, therefore changing its radius. So you can see that with all these examples here. With lithium, it lost an electron, so then it gets smaller. So, as you'll see here, ionic radius is very similar to atomic radius, making it very easy. Except for, as you see in period 3, if you go from sodium to silicon, it follows the trend. However, when you get to phosphorus, its radius is bigger than silicon, which breaks the pattern. And that this purple line here represents that break, but then it continues, the pattern continues on, so that's the only difference. Okay, the third one, reactivity. So as you can see here in sodium, there's lots of shells, and then there's one electron, only one electron on the outer shell, which makes it more reactive because it's easier for the electron just to be pulled away by another element. And then with aluminum here, it's surrounded by a lot of shells as well. So this last shell, even though it has 3 electrons, it's still more reactive because this last shell is so much further away from the nucleus. So basically from this pattern, you can see that the more levels or shells of an element has, the more reactive it will be. So francium is the most reactive because you can see here, this is francium, how many shells it has, so many shells, and the last shell only has 1 electron, making it super easy just to grab onto another element. And this is also why the alkali metals over here are so reactive. Okay, reactivity continued. So the one we just went over before was for metals, but it's actually the opposite direction for nonmetals. So nonmetals react by gaining valence electrons until they have 8. So therefore the nonmetals with 7 valence electrons, which are the halogens right here, are the most reactive, like fluorine. So then also atoms near the top can capture electrons most easily because the valence electrons are closer to the nucleus. This trend, however, does not include the noble gases over here because they already have full S and P sublevels. Okay, now ionization energy. So ionization energy is just the amount of energy required to remove a valence electron from an atom. Pretty much what we were talking about before. So, in other words, how much energy it takes to make an atom an ion. So small atoms like hydrogen right here, the valence electrons are super close to the nucleus, so it takes more energy to pull them away. And francium over here, since the valence electrons are so far, it takes less energy. So more energy that way, less energy in the bottom left-hand corner. Okay. And the last one is electronegativity. So it's how much can an atom attract shared electrons to itself. So the attraction of valence electrons in larger atoms, is weaker than the small atoms. So larger atoms lower in a group, like over here, are less electronegative. Okay, that's pretty much it. Summary. So basically all these patterns have to do with the electron's distance from the nucleus. That's pretty much it. Thank you.